All right, hell yeah. We're going to try to burn this one down. 5 minutes. All right, so we have a child's pogo stick, you know what I mean? And this is an energy problem, you know what I mean? Like right here, there's no energy in the spring. Right here, you're compressing the spring. Okay, so what we're going to do is instead of energy, we're going to solve it as an F equals ma using Excel. And so how this works is, well, like the one thing I wanted to do, like springs seem complex, you know what I mean? Because the function for the force is negative kx. It just seems like too much to handle. And then you have a spring constant, in our case, is 25,000 Newton meters. So what I just want to do is say, hey, what's the force due to gravity on this kid? It's 25 kilograms in weight. So there you go. And then so the force is just mass times the gravitational constant. Just times gravity, 9.8. So we get 245 newtons. Cool. Now we can analyze what the hell's a spring do? Well, its force is just this number times the distance that you compress the spring. So if this kid just sags onto the pogo stick, just kind of balances, and you've done this with like a mountain bike, we all have full suspension mountain bikes, hopefully, because they're rad. But anyway, you sit on them, and then your suspension sags, and it sags because you're putting your just force of gravity. So in this case, the kid's 245 newtons. So we want to know when, like how much sag it is. So you just make this mg equal to this negative kx. You know what I mean? And when you do that, you find that, I really don't have that on here, but that's literally all you do. So to get this, and what we want to do is find x. So if mg is equal to negative kx, well, you're just going to do mg divided by k. So you're going to have 245 divided by 25,000. So the whole thing is just kind of do this in your head. You're going to have about 250. So you have 25 with a 0 and then 25 with three zeros. The 25s go away, and you're left with 100 divided by 1,000. Whoa. 100 divided by, I guess, no, it's a little more than that. I don't know why I can't do this in my head. Damn it. So you got 2, 5 with 1 0 and then 2, 5 with 3 zeros. Yeah, you're going to have a difference of 2 zeros. So that's why this is really close to 0.01. It's really close to 0.01, but it's 0.0098 meters. That's 10 millimeters or 1 centimeter. Cool. So that just shows you, oh, okay. You know what I mean? So if I compress this spring 1 centimeter, that's like the weight of the kid. If you compress it 4 centimeters, you know what I mean? That's going to give you 4 times the weight. And then so our problem says, hey, we're going to compress this spring a tenth of a meter. You know what I mean? How far is that? That's actually significant. That's going to be 10 centimeters. That's legit. Anyway, I don't know why I'm getting hung up on that. How long is a meter? 10 centimeters. Yeah, 10 centimeters is 10 centimeters is 100 millimeters. So that's how much we're compressing the spring right here. That's 4 inches. So we're compressing the spring, because a meter is 40 inches. You know what I mean? Basically, and a tenth of a meter is 4 inches. Holy today, that's the hardest thing about Americans doing engineering. It's just like we didn't live in Canada all our lives. Okay, so anyway. And so we're going to compress that. So we can actually find the force, once we compress. Like once this kid compresses it, we're going to find that force. And it's going to be 0.1 times this. This is going to be 2,500. So we're going to have a force of 2,500 newtons. Cool. Now what the hell does that even mean? Well, you use our equation that says, hey, we're basically going to have a force of 2,500. And we're still gonna have this gravity force. So you know what I mean. So maybe we'll start with a force of 2,255. See how that right there? This was at our starting position. You know what I mean. Once the kid compresses this all the way, 0.1 meters, we're gonna have 2,500 newtons pushing up from the spring, but at the same time, the kid's got weight and the earth is below him, so we have a little bit of gravity, 245 pushing down. But this is our net force pushing up, 2,255 newtons. So now what the hell does that mean? Well, we use our equation that says, hey, if you can find a force net, like if there's a net force in a direction, hey, that object is moving. And not only is it moving, it's changing its velocity. Because this whole equation is F equals ma. It says, hey, we identified the force net, and we've identified a mass, and so that means that mass is going to accelerate. So anytime you write this F equals ma, definitely rearrange it and write A is equal to F over m. It gives you two equations. You know what I mean? It doesn't look like you got two equations, but hell yeah. Because now we're going to be like, hey, this is the acceleration. Is going to be this F divided by m. And you know what I mean? This is how you set it up in Excel. You say, hey, I'm going to say this is the force divided by the m, and then throw these $2 signs. It's a function, it's F4. You get type F4, you get those dollar signs. See? F4, get the whole array of dollar signs. Got to be both, though. Okay, hell yeah. All right, so now what the hell does acceleration even mean? Well, write this. Acceleration means change in velocity, change in time. Okay, cool, but what does that give us? Well, it says, yeah, that's the other thing. It's crazy. You know what I mean? Because I wrote, I guess I didn't write anything. We'll get to that later. But it shows, yeah, like right off the bat, literally. It's a bummer. I didn't write that down. I'm actually going to take a pause. Because, yeah, that's a good place to take a pause. Alright, hell yeah. Sorry I wasn't ready. But yeah, I had this whole diagram. So, I think it's really smart to be like, hey, anytime you have a map, just draw it like as a freaking square. You know what I mean? And throw it just in space. Pretend like this thing is literally in outer space. Because the only forces that are around us are due to the Earth because it's huge and it's below us. So that's this mg. And then for our problem, hell yeah, this is the pogo stick. You have a spring now, and the spring has a negative kx, and that drives me insane. And I just kind of figured it out for myself. Be like, okay. You know how like you have like a rope and you do like a free body diagram and like the tension on the rope's always pointing out? Well, let's say you just have a spring and the force is always pointing away from the direction of spring. I think we can handle that. You know what I mean? An object pushes into a spring and the force is always, how you draw the force is just always outward. And why it's negative kx is because this x becomes negative. You know what I mean? Because when the spring's at rest, it's just up here. But once we compress that spring 0.1 meters, we're doing that in the negative direction. You know what I mean? So hell yeah, let's say we like blasted rockets off into space with a spring. You know what I mean? We want to go into the positive direction. You know what I mean? But you'll compress that spring in the negative direction. So that's where this, and then these negatives cancel, and then hell yeah, we can send something into orbit. In this case, we're sending this kid not into orbit, but about 6 inches off the ground, enough where he thinks it's cool. Okay, so and right off the bat, this spring constant is huge, and so if you have a huge spring constant, it says, hey, if you compress this spring 1 meter, you're going to have 25,000 newtons. I don't even know what that is, but it just sounds like a large amount of newtons. And divide by 4, you know what I mean? That's going to be about 5,000. That's going to be 5,000 pounds. So literally, if you had like a pogo stick that you compress 1 meter, you'd have 5,000 pounds. That's insane. Right here, it's just 2,500. That's significant because divide this by 4. You get about 600 pounds, you know what I mean? So yeah, you got 600 pounds of force pushing back up at you. All right, and do you think this is going to be forever? You know what I mean? Because here's what I did. It's like, this is what we hope, F equals ma, and then we identified a force, and then we rearranged the equation to say, hey, we want to find the acceleration on this little box. And so we go F equals m. And then we see a force of 2,255. Whoa. Yeah. Because you see how these forces cancel. The spring is a hella force, but you always have gravity pushing down. So you know what I mean. And so yeah, we get this 2,255 newtons divided by the mass, 25 kilograms. So we get 90.2, just call it 90 meters per second squared. And what the hell does that even mean? Well, it says, hey, if we continue having this force for a full second, we're going to change our velocity by 90 meters per second. And even Canadians probably don't know too much about meters per second because they drive in kilometers per hour. But anyway, multiply by 2, or just 2.25, and you get 200 miles per hour. So if you have this force for 1 second, your velocity is going to change by, you're going to go from 0 to 90. You're going to go to 0 to 200 miles per hour in 1 second. But that's not the case. The kid doesn't, you know what I mean, go at breakneck speeds because the toy is not that cool. So what happens here is that we're going to have this acceleration, but just for a very fractional amount of time. And the second we move just even a little bit, this force due to the spring is depending on where you are between here and here. So if you're here, it's just half that. And if you're here, it's 0. And it's linear. So we're going to say at least the force of the spring is going to be half that. And I'm just going to say, hey, let's just say that the acceleration is half of 90, and we're just going to say it's 45. But guess what? How long is this force going to actually take place? And I guess I just have to give you this 0.05 seconds, because that's what we found out from Excel. That you're only going to have this force for 0.05 seconds. And so if you have a 45 meters per second squared times seconds, and we'll get to that in a second. But yeah, you only have a change in velocity of 2.25, and that's actually the answer that they want. And so let's go back to how we found that. And then so just right here, we get that's gonna be our max velocity, 2.88. Oh, you know what? So we actually get a higher velocity, because if you just do this, I mean, do you want to learn how to do it just like the normal way first, or the Excel way? But 2.85 meters per second is your max velocity, and 2.84 meters per second is we'll go back to like where they actually want this. So they want to know the velocity right when before the kid blasts off. You know what I mean? Well, what's your velocity? That's going to be your max velocity. At the top, it's 0. Kids stopped. Kids are also stopped at the beginning. But there's going to be the spring force. So what happens is there's a point where, yes, the sag. Remember how I said this? Like if you just sag onto a pogo stick, that spring is going to go about a 1 centimeter. Well, so at that point, the spring's not pushing you up anymore. You know what I mean? And so yeah. So you're actually only increasing your velocity from negative 0.1 meters to so that's 10 centimeters, from 10 centimeters to 1 centimeter. You know what I mean? That's the only time you're going to. So if we go back to here, you know what I mean? These are in meters, and so once we get to that 0.009, you know what I mean? 0.01, 1 centimeter. This is going to be our max velocity. Actually, it's that one. And then we're going to actually reduce our velocity. Okay, so how do you set this up in Excel? Is you say, hey, your time's 0, and then your position's -1. You just insert these, and then your velocity is 0. That's what you insert. And then we just use this equation that says F equals ma, and you just sum up. Well, we already did that. We already, you know what I mean? That's why this one was real important. Draw your picture, and yeah, you got the force of the spring going up, and then the weight going down. So what do we have here? Is we have the mg, that's 25 times 9.8, that's that part, and then plus, you know what I mean, the spring constant, well, it's this negative kx, so we put in the negative sign, 25,000 times our x, but our x is negative, so it's a negative times a negative, and so that's going to be in the positive direction. All right, hell yeah. And oh, I was like, trying to take a pause here because I was just like, well, shouldn't this mg be negative too? All right, hell yeah, that was tripping me up. I couldn't see this negative sign right there, but we do have a negative. Yeah, yeah. So the mg, the gravity is in the downward direction. You know what I mean? So there you go. So your mg is negative. So if you sum the forces, you'd have negative mg plus negative kx. And it seems like you're subtracting two things, but if this is negative, it becomes positive. So you have negative mg plus, you know what I mean? It's 25,000. All right, so there you go. But it should be this simple. Now the other stuff, I don't know. It doesn't get too complicated. Oh, I better push escape before I lose it all. Okay, so here's your net force, and it's pushing up right at the beginning, right at your initial position. So now we want to rearrange that F equals ma equation to say A is equal to F over m. We find our acceleration. That's super simple. You just take this force divided by the mass. And just make sure to do the F4 dollar signs. You know what I mean? Because the second, what we're going to do is we're going to pull all these formulas down, and you don't want to, have this get drugged down. You know, that's why you keep it with the dollar signs. Okay, so now this is the fundamentals of doing any physics. You're always trying to find acceleration. So what you should do is write the definition of acceleration. Acceleration is change in velocity divided by change in time, or change in velocity per change in time. So just write A is equal to dv over dt. And the cool thing about this is that as long as acceleration is constant, this is like a legitimate equation. For any point, you can find the velocity, you know what I mean, or how much the velocity is going to change given amount of time, you know what I mean. So anyway, but what we have is a small change in time, so that's why this works. So we rearrange this equation because we want to find our change in velocity. You know what I mean? So our velocity is 0, and we have an acceleration. We found the forces. So this is going to give us a change in velocity. And so how does that work? Well, it says dv, so bring the dt upstairs, and now we got acceleration times our change in time is equal to our change in velocity. Now, we want to make our change in time kind of small, 0 to 0.001 seconds. You know, I mean, depending on the problem, you might have to make at least a tenth of a second. Sometimes you can do a 1 second if it's a slope, you know what I mean? But you figure that out. All right, but we have thousandths of a second. And so what we have here is we have our acceleration, that's this A, times our dt. And so our dt is just this time minus this time. It's just the difference between these two times. And then this will get pulled down. You don't have to write it this way. You could just literally say your dt is equal to 0.001, you know what I mean, a thousandth of a second. And then do the dollar signs, you know what I mean? And then you would go this, you would say this is equal to A times this, dollar sign it, and then you got your change in velocity. But right here, booyah. So now if this is our change in velocity, we started at 0. So right here, you're going to go, this equation is 0 plus that. Your initial velocity plus the change in velocity. And the cool thing about doing this in Excel is like, hey, it doesn't rack your brain. You're just like, okay, that made sense. Now I know my new velocity because I accelerated for a thousandth of a second, and then booyah. Okay, but now we want to know our position, and to do that, we need to find our velocity average, and I'll tell you why in a second. But how we find our velocity average is just add these two up and divide by 2. You add them together and then divide by 2. And that's because if you have 0 to 10, that's easy. Average velocity is 5. But let's say you have 10 to 20. You know what I mean? Your average velocity would be 15. How do you actually get 15? You add 10 plus 20 is 30 divided by 2. That's why velocity average, always a good one to do. And know that it's just add them up, divide by 2. Cool. Okay, so why did we need our average velocity? Well, it was the same reason we kind of needed we needed to know that our acceleration was kind of a constant. And our velocity is either 0 or it's 0.09. So like, what are you going to choose? You know what I mean? You could just choose 0. And you don't have to choose your average velocity, but it just makes it way more accurate. You know what I mean? And so So right here, we're going to say the next equation is the definition of velocity. We're saying definition of velocity is change in position divided by change in time. And this is an equation, like I said, if velocity is constant, this is an equation. You know what I mean? You can 100%, like if you know you drive 60 miles an hour, you can find your change in position at a half an hour. You know what I mean? You'll know it's 30 miles, you'll be 30 miles away. So as long as your velocity is constant, this is an equation. And it's an equation for us because our change in time is real small. Cool. So then rearrange this equation because we want to know the change in x. We want to know our change in distance, and that's going to be our velocity average. Like I said, 60 miles per hour, and then times the time, half an hour. Hey, it looks like we're going 30 miles. 60 miles per hour times half hour, 30 miles. So anyway, that's the same thing we're doing here. So our dx is our velocity average times our dt. And again, you don't have to do it the way I do it, this times this. You can just say, hey, for this problem, my dt is 100th of a second. But anyway, it's nice to do it this way because you might have to change your dt, because usually I start with like a 10th of a second. This was 100th, and it was just still too, like even just right here, my it was like right here, 0.05. That's what I said. At 0.05, the kid's going to be airborne. You know what I mean? So that's just only like 5 values. Well, we're going to get 50 values before that happens. Okay, anyway, we got our dx. Guess what? Our next dx is just, so this equation is our x initial plus our change in x. And our change in x is in the positive direction. And why is that? Because our acceleration is in the positive direction. You know what I mean? We can still be in the negative x direction because we compress this spring, but our acceleration is going into the positive direction. Cool. So anyway, so once you got that, I mean, you brought down the velocity in this, then you would take this and then bring these down. So you just make sure everything's the same, and then you'll just bring it all down. Don't bring your times down because to get this time, you'll do 0.00, and then you can drag this down. And if you want to see that, it's like you go 0 and then 0.1. Oh, sorry, 0, enter, 0.1, and then you grab them both, and then you can pull them down, and then it'll do that. Okay, so anyway, and then is basically like you just graph the whole thing. So our x is negative, and we're going to go down until our x is 0. The kid's going to be right there. And then that's what we did. So we go down until our x becomes positive. Perfect. Right there it becomes positive. But then something special happens at 0.0098 is that we get our, I'm sorry I did, this one shouldn't be filled. Because at this, our acceleration is now negative. You know what I mean? Our acceleration was positive here, but now it's negative, so we're actually slowing down. And then we're slowing down hella, and then we're really slowing down. And then, hey, remember that negative 250? That's the force of gravity. You know what I mean? So that's like the spring constant. The spring let go. He is going to go airborne, and then negative 250 is the only force on him. Now, with this equation, this equation is set up like he's attached to the spring. So if we just took this equation farther, it would say, hey, the spring's going to pull him back, and that's not the case. So then what I did is I took a pause, wrote all these parameters again, and say, hey, we're just going to set it up again and say right now our position is at 0. Our velocity, see, I just said, hey, our velocity is over here. We're going to start at this time, 0.053, and then go down there. But now our force is just gravity. Literally, the kid's, in airborne. And so I just wrote 0.2. So the gravity is negative 245 newtons. That means the acceleration is just mg. Or the acceleration is just g. The acceleration of gravity is 9.8. So if the kid's going 2.8 meters per second, let's say the kid was going 9.8 meters per second. Well, in 1 second, he's going to stop. he's going to be at the highest point. But he's not going that. He's only going this. So it's not going to take him very long to stop. And when will we know that he stopped? When this velocity becomes 0. So all right, we do the same thing. So acceleration is this force divided by the mass, and I just did 25 for here. And then rearrange the equation for acceleration. So we get dv is a times dt, and that's going to be this acceleration times the change in time. And we get this amount of velocity change. So then this equation is the initial plus this change. And this change is a negative. So we actually have some velocity, and we're actually going to be slowing down every time. And so we're going to go over here. We're going to find the velocity average. That's going to be this higher velocity plus this lower divided by 2. Velocity average is a little bit lower. And then rearrange the equation for velocity. Velocity is dx dt. So we're going to say, hey, velocity times dt is just dx. So that's going to be our change in position. And that's going to be our velocity average times this. Booyah. And then what does this say? This says that our change in x is positive. See, yeah, we're still going in the positive direction, but look at this. It's getting a little bit smaller. 0.0028, 0.0027. Anyway, so this is your x. X is going to be x initial at that 0, that datum, plus your change in x. Okay, and then you just, same thing. Pull them all down so you're just so all these are just in a line, and then you can just pull the whole thing down, pull all the equations. And then so what we're going to go until we find where velocity is 0, and then look at our height. See, because we are still adding some height, even though our velocity. All right, so we're going to go till velocity gets to 0. All right, booyah, right down here. Velocity is 0, and see, we're barely adding any height at the top, but our height is 0.42 meters. And if we go to the solutions manual for this problem, it says 0.41. You know what I mean? So we don't get 100% accurate. This actually overshot. You know what I mean? Because it probably shows the force of the spring being higher than it is. Because this force of the spring is the dominant thing. Where, you know how I said the force of the... But anyway, so this is the acceleration versus time. Anyway, we're about done. And let's look at the solutions, how they found it. They said 0.41 meters. We found a max velocity of 2.88, you know what I mean, as a kind of our max velocity. They found 2.85. The velocity right before the kid takes off is 2.84, so it's slightly less, and we kind of talked about that. Now let's figure out how to actually do these problems simply, you know what I mean, because how I solved it was using F equals ma. And to do that, you know what I mean, it's kind of nice to use Excel, because you're going to have a different net force at every change in time. But as long as you can add them up in Excel, you know, you can figure out exactly where this thing's going, what its velocity is, and what its position is. You know what I mean? You have a total function of it without an equation. All right, so with energy, energy is cool because it says, hey, the energy at the beginning, energy at A is equal to the energy at B is equal to energy at C. And then so this kid's going to be in the 3 position. A down there, B right before he takes off, and then C at the top. All right, so hell yeah. So this is literally what the energy equation says. And why did I write check marks? Because they're not equal. If friction is just like taking energy from the system, energy is still conserved, but if you have like a ton of friction, all that energy went into heating other molecules and making them move. F equals ma says I have mass and I have movement. You know what I mean? So if you have friction, well, hell yeah, all that heat is vibrating at the molecular level, a mass of like metal and blah, blah, blah. And that's where that you know, so F equals ma still applies even at the atomic level, you know what I mean, at the level of atoms. It doesn't apply probably at the quantum level. That's where you get into quantum physics. But literally, if you're dealing with atoms, even very small atoms, F equals ma apply. You might not be able to, you know, use an Excel sheet to figure out all the motion of those mass and the vibration of heated particles. But anyway, this says as long as energy isn't leaving the system, and right here, this is the definition of a closed system. We have the spring is attached to the kid on a pogo stick. You know what I mean? So nothing is leaving. So the energy at this position, same. All right, let's do it. And energy is a combination of potential energy. You might have seen this, MGH. You can write it MGX. I like to write it MGX now because a lot of other things are a function of its position. Because a spring constant is the energy is 1/2 kx squared. So that's going to be the same value of x as there and there. Now at the beginning, 1/2 mv squared is kinetic energy with its velocity, but there's no velocity at the beginning, so that's 0. Okay, at the position B, where the kid's just ready to take off, the spring isn't doing crap. Same thing here. Spring's not doing crap. It's totally out of the system. So let's and we're saying this is our datum, so there is no more potential energy. Let's and in here. Usually potential energy, like if water is above a dam, well, the water is way up high. But in this case, our datum is 0, so this is actually a negative. So this is actually negative potential energy. But right here, the potential energy is 0. We're setting that. And then at the height, the potential energy is max. MGH. MGH is that height of C, height at C. And that's one of the questions. They want to know how high this kid is. Cool. And velocity of B. Like I said, it's not the max velocity. We'll go over that. Anyway, so at each of these places, you have the potential, kinetic, plus maybe like the spring. The spring's not in the B and C, so we just have potential, kinetic, potential, kinetic. Okay, so we have basically three equations, and well, we have 2 equations, 2 unknowns. We know this side, and it's going to be equal to this, and it's going to be equal to this. Our unknowns are VB and XC. So right now we can solve for either one. It doesn't really matter. I solve for VB first. And so how I do that, I just keep all this stuff right there, and then just divide by this half, divide by m, and then I can take the square root of it. That's all I did. And then just you throw the numbers in. And this goes back to chapter 1 physics. You know what I mean? Mass is 25, 9.8, negative 0.1. So what you do is you just guess. You know what I mean? So right here, let's take this one. So if we got 0.1 times 0.1, we're going to get 0.01. So that's going to be 2 zeros gone from this, and you're going to get 250. And then we're going to half it. That sounds like 125. All right, moving on. This, you're going to go 225 times 10. That sounds like 250. Oh, but then take away a 0. So this is going to be 25, negative 25. Oh, didn't we say this was 125? So we got 125 minus 25. That's 100. Cool. All right, and then we're going to divide it by, this is 25, well, I don't know. Well, let's say it's 25 times 5. That's it's close enough to 100. And then we're going to move the decimal place. So this is 10. This is basically 10. So we have 100 divided by 10. That sounds like 10. This is the square root of 10. And it's actually, if you caught it, this was actually, 5 times 25 is 125. So this is going to be a little bit bigger. So it's going to be not the square root of 10. It's going to be the square root of 8. 8.04 to be exact. And you got, so that was just a quick mental way. So once we plug all this crap into our TI-83 or whatever you got, you'll get the right answer. You know what I mean? Or if you messed up, you'll know why. Okay, cool. And once you got velocity at B, then you'll use this equation, and then you can insert this into your calculator, and then you can make these two equal. And then what we're going to do is, take this and then divide by this mg, and you'll get this. So, and then the m's cancel, and then I just bring the 2 downstairs, so I get VB squared over 2g. Booyah, booyah! You get 0.41 meters. Okay, and I think the trickiest thing though is to actually figure out. Oh, no. Yeah. Well, this was the max velocity. You know what I mean? So, using the energy equation, We just have a new point. You know what I mean? That's the thing. If we go back to our, this was A, this was B, this was C. If we can recognize, and the only way, that's the part of the problem, is like, well, what's the fastest speed? You just had to figure out that once you get above this sag, like, yeah, the sag is going to be 1 centimeter. But once you're above that, the force of the spring gets real weak. I mean, if you barely move a spring, the force on it's just hardly anything, and you know what I mean, compared to the weight of a person. So for that 1 centimeter, the spring does not no longer forces the mass up, but gravity definitely pulls it down and slows it. So you're gonna have that. So that they just want you to figure that out, that at 1 centimeter, or 0.0098 meters, 9.8 millimeters, however you want to say it, at that point, that's going to be your fastest velocity. So I'm just gonna say, hey, that's D. As a new position, and we're just gonna say, hey, so now we have this new energy position. So the energy at D is equal to the energy at A, B, C. And we're going to do the check marks because there's no friction. In this problem, no friction leaves the system. And, I mean, just think about it. Let's say you did have energy at E, but between A and B, there was friction loss. Well, you're going to say energy at A minus that friction loss is now that new energy at B that we can calculate. You know what I mean? Because that energy went into the frictional heat of metal or the road surface, blah blah blah. You know, I mean, we can't measure that, but we can calculate it, but it's no longer part of our system. So that's how you take out energy from the system, but still recognize that the conservation of energy always applies. The energy at one point is going to be equal to the energy at the other point, as long as it's not like getting lost due to friction. And usually friction is like the only one that loses energy from the system. But you know what I mean? I mean, literally the kid could get like separated from the pogo stick, you know what I mean? So now you have the system got broke up into two pieces, you know what I mean? So you do have that, Okay. So anyway, so the energy at D has to be the energy of all these, and we know the energy at all these, but and I should have done a better job of um, actually, I mean, because if you just know that this energy is in joules, it is in meters per second. So let's just do that. So this is mg, and we said this was about 250, 25 times 10. And we're going to multiply that by this height, which was like 0.5. So you got 250 times, maybe it's 240 divided by 2. So you're going to get 120 joules. And I think in the book says it's like 100 joules. You know what I mean? So right there, there's your energy at any point is like 100 joules. Hopefully that's the that makes sense. But anyway, and then so what did we do? So we said we got to get, so anyway, so we got the potential energy, mg(xd), plus the spring still applies because the spring is still doing something at this xd. It's hardly doing crap, and I think and in this case, it's not equal. These are not equal because it's force times distance. So that's where I thought this was like interesting. I thought maybe these were equal, but those weren't. Only mg kx is equal. You know what I mean? So it's the force is equal. So the force of gravity is mg. The force of the spring is just kx. You know what I mean? So those two are equal. All right, but the energy equation says potential energy, mgxd plus this velocity. And now this is what we don't know. We don't know this max velocity. X's are the same, and everything else we know. And we know this velocity at B. So now we'd have to just bring this over here, bring this over here. That's what we do. And I guess I just did it yeah, and then solve. I mean, basically, all you got to do is just solve for VD. Do whatever you want to do. How I did it is like I recognize that there's basically a mass in all these, except this one. So I'm going to go K over M. I'm going to divide K divided by M, and now I can just cancel all those masses. Got it. Okay, now I'm going to multiply by 2 throughout this entire thing, so all these halves go away. And now I just get VD. And That sounds bad. But anyway, and then you, yeah, so this is just VB, VB squared. And then, like I said, K over M, but without the half. So there you go, kind of simplified it. And now I can just take VB squared minus this thing first, and then minus this thing, and then take the square root. And again, you know what I mean? Like, let's do that same physics one. You know, even though this sounds complex, so we have what do we say? 2.8 squared. That's almost 3 squared. Well, we kind of know what that is. We kind of know that that was 8. And now we're going to go over here. This is 0.01, and we square it, so that's going to be like 4 zeros gone. So we're going to go 1, 2, 3. This is going to be 2.5. Let's say it was 25 divided by 25. That's just 1, but it's 2.5. So this is 0.1. So we have negative 0.1, because this negative goes away because we're squaring it. So we got negative 0.1 right there. Okay, you know what I mean? So at least before we put it in our calculator, we get kind of an idea of what's going on here. And then here we have 10. You know what I mean? So we can, and this is 0.01 multiplied by 10. This is basically 0.1. So a tenth, 2 times a tenth. Hey, this is going to be plus, because there's 2 negatives, plus 2 tenths. Okay, so we plus 2 tenths minus 1 tenth. So we're going to get a result of plus a tenth. And does this make sense? Now we take 8 and turn it into 8.1, square root it, and we get our new velocity of 2.85. You know what I mean? So our velocity changes by very little, but it is max right there, 2.85. And if we go back to the answer, you know, in the book, this was that 2.85 that we got. This is the 2.84. So velocity is 2.84 once the kid's ready to blast off. But there's a point 1 centimeter below this where the velocity is going to be the max, and that is 2.85. And I'm done with this problem, but it just shows you, hell yeah, set it up in Excel. I really enjoy it. And there's just absolutely no way I'm going to do a 5-minute problem. So I apologize for saying, oh, I'm just going to do this in 5 minutes. But at least I did the problem first, because I probably spent an hour and a half on this. You know what I mean? And so this video is tolerable, and I'm pretty happy with this one. So thanks for joining me, and guess what? That's a video.